Hi, this is Jerry Pinter. Welcome to Chapter 12, the Thermal Properties of Matter. In Part 1 of this lecture, we'll be looking at the atomic model of matter. Chapter 12 is a rather lengthy chapter and is one of the more technical chapters in this textbook. So as such, I've broken it up into 5 parts that we'll be covering in 5 separate videos. In this Part 1, we'll be looking at the atomic model of matter. In Part 2, we'll look at the ideal gas law and the PV diagram. Part 3 is the first law of thermodynamics for ideal gas processes. Part 4 is on specific heat, and Part 5 is on phase changes, heat of transformation, and heat transfer. So let's get started with Part 1 of this lecture on the atomic model of matter. So we're going to start with a very simple and basic model of the atom. And once again, we see this word model where scientists use a simplified description of a complicated system so that we can understand it better and learn how it works. So in this case, we're taking something that is actually quite complicated, and that is atomic physics, and we're going to boil it down to a very simple model that will help explain some of the properties of matter. So the simple atomic model that we're dealing with here has the following points. Matter, all matter, consists of individual building blocks called atoms. There are more than 90 different kinds of atoms. These are the so-called chemical elements found in the periodic table. Atoms consist of electrons, protons, and neutrons. The atomic nucleus contains protons and neutrons and has positive charge. Electrons have negative charge and orbit the nucleus. So to see what this means, here's an example of a model of an atom. This happens to be an atom of the element boron. So we can see in the center here, this is the atomic nucleus. And this particular nucleus contains 5 protons and 5 neutrons. Now the protons have positive charge. So they attract the negatively charged electrons, which are seen orbiting around the nucleus here. And there are 5 electrons, 1 for each proton. If we look into the, kind of drill down and look at the atomic nucleus a little closer, there are a couple features here that are going to be useful to us in this part of the lecture. So remember, the nucleus contains protons, which in this model or picture here are shown as the blue spheres with the little positive charges indicating they have positive charge. The number of protons in this nucleus is given by what is called the atomic number for the element, and the atomic number is also abbreviated as Z, although we won't see this nomenclature until, or this notation until later in the textbook. If you take Physics 102, when we study nuclear physics, you will see this Z. But the atomic number just means the number of protons. Likewise, the nucleus contains these red spheres in this picture, which are the neutrons. And the neutron number can be designated as N, an uppercase N, which just tells us the number of neutrons in this nucleus. If you add together all the protons and all the neutrons, you get what is called the atomic mass number, A. So A is just equal to Z plus N. It's the total number of what are called nucleons, and a nucleon is a particle in the nucleus, which of course are protons and neutrons. So both protons and neutrons are considered nucleons. So some of the notation, again, we're not going to really use this as much in this chapter as we will later in the textbook, but the notation for this is, for example, for carbon, the element symbol C is shown here, and then there's out in front there's a subscript down here, which is the atomic number 6 for carbon, and then this number up here, the superscript, is the atomic mass number. A is 14 in this particular type of carbon. One thing we could see here is that the question comes up, how many neutrons would this carbon have? Well, the answer would be 8, because we know there are 14 total protons and neutrons, and we know there are 6 protons. So 14 minus 6 is 8 neutrons. Now, this is somewhat redundant, this notation, because the atomic number 6 always refers to carbon. In fact, carbon is defined by a nucleus that has 6 protons. So the 6 here doesn't really need to be shown. So sometimes this is just shown as a C here with the atomic mass number 14 up here. And this is also can be written out as carbon 14. And that's the way we say this notation, carbon 14. So here's a periodic table of the elements. And again, this is not something we're really going to study in this chapter of the course. Again, if you take Physics 102, you will talk about atoms and the periodic table late in the course. There's a chapter dedicated to this in your textbook that we will not study in Physics 101. However, the periodic table of the elements is basically a list of all of the elements that exist. There are roughly 92 naturally occurring elements. I say roughly because 93 and 94, neptunium and plutonium, actually do exist naturally, but their abundance is so tiny compared to, uranium here that oftentimes these are said to not really exist naturally. So these elements down here that are come after uranium are called the transuranic elements, and they are typically manufactured. They're man-made elements. But the key thing here is that all of the matter on Earth is made of these elements that are on this periodic table. And what we're looking at right now is the atomic number. Remember, tells us the number of protons. So this number above the element symbol, this is hydrogen, which is element number 1. This is helium, element number 2. That is the atomic number. And so the periodic table, the elements are listed in order by their atomic number. So it goes 1, 2, and then here we see lithium is 3, beryllium 4, boron 5, carbon 6, and so on and so on. By the way, the organization of this chart or table into rows and columns is something that will be talked about in Physics 102. So knowing the basics about the nucleus with the protons and neutrons in it, we can come up with a way to calculate the mass of an atom using something called atomic mass. So it turns out that almost all of the mass of an atom is contained in its nucleus, which contains protons and neutrons. So what this tells us is that the electrons, which are orbiting around the outside, are very light compared to the protons and the neutrons. In fact, an electron is about 1,800 times, almost 2,000 times smaller in mass than a proton or a neutron. So they really don't contribute much of anything to the mass of an atom. Therefore, when you lift something up, like a pencil, or a heavy weight in the gym, basically what you're lifting is you're lifting up the nuclei. That's where all the mass and the weight comes from. So we saw that the atomic mass number is called A, which is the number of protons plus the number of neutrons inside of the nucleus. So it turns out also that each proton and neutron has approximately the same mass. All right, there is a subtle difference in mass between a proton and a neutron, and again, this is something that you'll work with in more detail in Physics 102. But for this chapter, you can consider protons and neutrons to basically have an almost identical mass, and the approximate mass of a proton or a neutron is given by what is called the atomic mass unit, and that's given the letter U, and you can see the atomic mass unit is an extremely tiny mass. It's 1.66 times 10 to the minus 27 kilograms. And this is not surprising because each proton and neutron is an extremely tiny subatomic particle that exists inside a single atom. So it's not a surprise that an atomic mass unit is this small. But the idea here is that instead of thinking about the mass of a proton or a neutron in terms of kilograms, we will just say it has a mass of 1 atomic mass unit, or 1 U. So with this, we can approximate the atomic mass of an atom given by its total mass is just equal to the atomic mass number A, remember that's the number of protons and neutrons, multiplied by U, which is the mass of each proton and neutron. So for example, let's look at this table here. I've just listed 5 different elements. The lightest element, hydrogen, has a single proton as its nucleus. So its atomic mass number, A, is 1. And here you can see its actual mass in atomic mass units, U, is 1.008. So it's not exactly 1, but for our purposes here, it's very close to 1. If we round this, it's within 1% of 1. Helium has 2 protons and 2 neutrons, so its atomic mass number is 4. You can see its actual mass is very close to 4. It's 4.003. So let's look at oxygen here. Oxygen has 8 protons and 8 neutrons for an atomic mass number of 16, and you can see its actual mass is 15.999, which rounds, of course, to 16. Iron, atomic mass of 56, actual mass 55.8. Again, very close. And here you can see uranium, which is one of the heaviest elements that are naturally occurring, has an atomic mass number of 238. All right, it has 92 protons and a whole bunch of neutrons, but a total of 238 of them, and you can see its actual mass is 238.03. So for the message here is that for this chapter and this course, we can estimate the atomic mass very accurately by just using the atomic mass number, which all we have to know is how many protons and how many neutrons. So going back to our periodic table of the elements, now we can see that for each of these elements listed here, we have, remember, the atomic number is the number on top. That's Z. That tells us how many protons. Underneath here, this number is the actual atomic mass in units of U, atomic mass units. So carbon has 6 protons. Therefore, it has, the main type of carbon has 6 neutrons as well, and you can see 6 plus 6 is 12, and that of course is very close to this number down here. This atomic mass under here, this number, is also equal to the molar mass in grams, which is something that we're going to talk about on the next slide. So let's take a look at something called the mole and Avogadro's number. So first of all, definition. What is a mole? A mole is the number of grams of a substance equal to the atomic mass of the substance. So let's look at some examples of what we call molar mass. So if we take iron, we look at iron here. Remember that iron has an atomic mass number of 56, and its actual mass, which we can get from the periodic table, is 55.8. So 1 mole of iron would weigh or have a mass of 55.8 grams. All right, this is the molar mass of iron. If we look at 1 mole of, this is hydrogen molecule. This is an H2 molecule. Well, hydrogen, remember, has a mass of 1, okay, atomic mass number of 1. But H2 means there's 2 hydrogens bonded together to form a diatomic molecule. So the molar mass of H2 would be 2 grams. So we just take this number here, all right, and again, you can use either one for this course. It doesn't really matter. You can use this number here or this number here, And we just have to add up, you know, if it's a molecule, we have to add up all the individual masses of each atom, and then we express it in grams, okay, not kilograms. Here's an example where we're actually using grams. Let's keep going, look at a couple more examples. So oxygen, the type of oxygen that you're breathing right now is molecular oxygen. It's not just oxygen atoms, it's O2. All right, it's a diatomic molecule with two oxygens together. So if we look at the table here, we see that oxygen has an atomic mass number of 16, and there are two of them. So 16 times 2 is 32, and then we just put the grams unit there. So that means that 1 mole of O2 has a mass of 32 grams. 1 mole of H2O, all right, this is water, has a mass of 18 grams, all right? There's 2 hydrogens, okay, so that means there's 1 plus 1 gives us 2. And then oxygen is 16, so we add that to the 2 hydrogens and we get a total of 18 grams. So a mole of water has a mass of 18 grams. Now, that is one definition of what a mole is, all right? A mole is therefore the number of grams of a substance that's equal to its atomic mass. There's another definition of a mole that's also very useful. A mole of any substance contains this number here, 6.02 times 10 to the 23rd molecules. And this is a very important number in both physics and chemistry. This is called Avogadro's number, and this is named after Amedeo Avogadro, the Italian physicist and chemist. So this number, instead of writing it out like this, we will call it N for number, and A with the A down here, N sub A for Avogadro. And what this tells us is that a mole of a, you know, whatever the substance is, a mole will always have this many molecules in it, okay? So a mole of oxygen has this many oxygen molecules, okay, a mole of O2. A mole of water has this many water molecules, okay? A mole, and so forth. Let's see. Oh, the other thing I just wanted to mention here is that obviously Avogadro's number is a very, very large number. 10 to the 23rd power, remember that's a 1 with 23 zeros after it, so obviously we're not going to want to write that out. We're going to express it in scientific notation. We can write the number of moles as a lowercase n. All right, and by the way, the symbol for mole is MOL. All right, it looks like mol. And remember, uppercase N, we're going to use that as the number of molecules. All right, so lowercase n is moles, big N is molecules. So the number of moles, N, is equal to the number of molecules divided by Avogadro's number. All right, so, and you can see how this works. If we have Avogadro's number up here, in other words, if we have 6.02 times 10 to the 23rd molecules, well, if we divide that by that same number, 6.02 times 10 to the 23rd, we get 1. That means we have 1 mole, okay? Likewise, if, you know, up here we have twice this number, which would be around 12 times 10 to the 23rd molecules. Well, when we divide that by Avogadro's number, we would get 2, because that would mean we have 2 moles, all right? So the number of moles, you can calculate it 2 ways. You can take the number of molecules and divide it by Avogadro's number, or remember, according to this definition here, we can also take the mass in grams of a substance and divide it by the molar mass in grams of that substance. And remember, the molar mass is this, calculated as we did up here. So we'll go through some examples that will use these relationships so we can see how to use them. So our first example, we have a bottle that contains 2.5 moles of water. So question A, what is the mass of the water? Well, we know from the previous slide that the number of moles, little n, is equal to the mass in grams of the substance divided by the molar mass in grams of the substance. So we're going to solve for this mass here. We want to know how much water do we have? How many grams of water? So mass is equal to N, which is the number of moles, times the molar mass. Okay, we're just rearranging this equation here. And N, little n, is 2.5 moles. And the molar mass is 18 grams per mole. Now remember how we got that. We're talking about water, H2O, so we can use this table here. The two hydrogens each have a mass of 1 gram, molar mass, and oxygen has a molar mass of 16 grams. So adding that together gives us the 18 grams per mole. So when we multiply 2.5 moles times 18 grams per mole, we get 45 grams. So that's how much water we have. Part B, how many water molecules are there? Well, here we're going to use our other definition of a mole. Remember that the number of moles is equal to the number of molecules divided by Avogadro's number. So the number of molecules, big N, is equal to little n, number of moles, times Avogadro's number. So we have 2.5 moles, and here's Avogadro's number, 6.02 times 10 to the 23rd molecules per mole. So multiplying these two numbers together gives us 1.5 times 10 to the 24th molecules. Let's look at another example that works a little bit differently. So in this case, we're told that a system contains 100 grams of oxygen. The question here, and we're going to assume, I should have probably put that in the problem here. We're going to assume that this is molecular oxygen, like the kind we breathe. So this is O2. So question A is, how many moles does it contain? Well, remember that the number of moles is equal to the mass in grams divided by the molar mass in grams. So we have 100 grams of substance, of oxygen, and we have to divide it by the molar mass of oxygen, which is 32. So remember, oxygen is O2, and so we have 16 plus 16, right? That's the atomic mass of oxygen is 16. So that's where we get the 32 grams per mole here. So 100 divided by 32 is 3.1 moles of oxygen. Part B says how many molecules of oxygen are in this system. Well, here we're going to use the other equation. Number of moles is equal to number of molecules divided by Avogadro's number. Therefore, the number of molecules, N, is equal to the number of moles, which is 3.1. All right, that was our answer from part A, times Avogadro's number, 6.02 times 10 to the 23rd. And again, just multiplying these two numbers together in your calculator will give you the answer. The number of molecules is 1.9 times 10 to the 24th molecules. Here's our last slide and example of this part of the lecture. A tank holds 5 times 10 to the 26th molecules of carbon dioxide, CO2, gas. Part A, how many moles of carbon dioxide are in the tank? So here we've got our number of moles is equal to the number of molecules, which is 5 times 10 to the 26th, divided by Avogadro's number, which is 6.02 times 10 to the 23rd. And this can be done easily on your calculator in scientific notation to give you the answer of 830 moles of CO2. Part B, what is the mass of the carbon dioxide? So to do this, let's calculate first of all the molar mass of CO2. So we know that carbon, we can look on the periodic table or look at a chart here or a table. We see carbon has an atomic mass of 12. Oxygen has an atomic mass of 16. So CO2 is 12, that's the carbon, plus 2 oxygens. So we have 2 times 16. So this is a total of 44 grams per mole. So that's our molar mass. All right, so the mass, remember that mass is equal to the number of moles times the molar mass. Okay, we did this in a previous problem a couple of slides ago. So we have 830 moles, that was our answer up here, times the molar mass of 44 grams per mole, so 830 times 44 is 36,520 grams, and if we want, we can convert that to kilograms just by dividing by 1,000. That's 36.52 kilograms. So that is part 1 of this chapter. I will see you shortly in part 2.